It's okay. Then I start.
Okay, if you're ready, so please start. Thank you.
Okay. Thank you for the introduction. Hello everyone, my name is Xiaokang Liu from Shandong University. It's my pleasure to present our work. Hollowed artwork and ornaments usually have beautiful appearance and a transparent sense of hierarchy. However, most of them express contours or an image by the solid or hollow part separately. None of them utilizes both solid and hollow space simultaneously, though it can bring novel artistic and aesthetic effects. Dual-shape tiling is a form of graphical art utilizing dual space well, and Escher's work is one of the most well-known, showing how two different types of patterns fit together in a plane. The two types of figures satisfy the mutual surrounding constraint, so the dual space of those tessellations can be seen as hollow and solid parts naturally. We observe that such fabrication problem can be reduced to a dihedral tessellation problem in the plane under the constraint. In order to conveniently and efficiently generate more interesting tessellation results, we aim to offer a system to design such a dual tessellation and model fabricable objects. Our goal is that, given closed patterns S1 and S2, compute two target closed patterns T1 and T2, the corresponding tessellation and fabricable model. We require that, first, T1 and T2 are as similar as possible to S1 and S2. Second, T1 and T2 form a dihedral tessellation under the mutual surrounding constraint. In fact, we recommend non-professional users to specify S1 and let the system suggest S2 from our database, since the compatibility between S1 and S2 has a significant impact on the quality of the result. Thus, we introduce fabricable dual Escher tessellations. This is a fabricated kitten, and the light source projects the shadows of swan on the wall and floor clearly. The shadows can express the shape of lily at the same time. Many researchers have conducted a number of related studies. Escherization was initially termed by Kaplan as a problem in computer graphics of telling a plane with a given closed figure. In a follow-up, they extended their method to admit two shapes tellings using dihedral telling patterns. Their method has too much loss of the shape meaning, especially without the assistance of texture. Quizme et al. Formulate Escherization telling as a maximum eigenvalue problem to allow more complex tail shapes. And recently, Lin et al. Proposed a framework integrating matching and wiping to generate Escher-like tails transformations for dual-shape perception. Our work has similar components addressing the dual-shape telling. However, ours is 3D fabrication-oriented, accounting for specific printability and application requirements. Zhou et al. Applied ornaments to fabricated 3D objects by synthesizing 1D patterns along curves with restricted topology. Thomas et al. Synthesized printable 3D patterns demonstrated by modifying texture synthesized to conform with the base surface. Chen et al. Synthesized filigree-like structures along surface. However, their approach synthesized a set of base elements allowing overlaps. The previous work helped us a lot, but it was far from enough to solve our problems. So we designed the following pipeline. Given a target shape and its quadrilateral polygon, we compute a rule-based four-tails pattern and find the best matching shape to the enclosed tail from a database by our system. Then we simultaneously map the two shapes such that they couple together while preserving their visual appearance, resulting in a dual Escher tessellation. The result can be mapped on a 3D object. After modeling and structural optimization, a fabricable model is generated and efficiently manufactured. First, I will explain tiling and shape matching. Here we adapt the 3 rules from the 12 heaven and hill tiling rules in Kaplan's work to generate our tiling rules. Our motivation behind this selection is that they generate quad tails, and we adapt these rules to make it more intuitive for placing the initial tiling polygon. The first is translation rule. We translate the P1 along the diagonal vector 1, 3 to obtain P2, then translate P1 and P2 along the diagonal vector 2, 4 to obtain P3 and P4 respectively. The second is reflection rule 1. Translate P1 along the diagonal vector 2, 4 to obtain P3. Flip P1 and P3 around a vector R. Then translate them along the vector to obtain P2 and P4 respectively. The third is reflection rule 2, which is similar to the reflection rule 1. And here, flip and translate. The last is the rotation rule. Rotate P1 around its tiling vertex 1 to obtain P2. Rotate P2 around the vertex 2 to obtain P3 and so on. These rules guarantee that the 4 tails are touching each other, enclosing an isolated area in their interior. And the rotation rule requires the tiling polygon to be a parallelogram. Then starting with input shape, we compute its candidate points and determine a quadrilateral tiling polygon by randomly selecting 4 points from them. Following these rules, the tiling patterns can be extended to the whole plane through repeated replications of the initial tail. We denote the enclosed space between the 4 tailed shapes by M. Then we use the triangle area representation to compute a best matching of S2 to M from our database. Then we compute the final patterns by shape morphing. In this step, our aim is to find an optimal transformations of S1 and M into T1 and T2. The objective function is lambda is the deformation weight, and F measures the degree of deformation from S to T. Omega is a shape similarity based on TR descriptors. Insect is a punitive so-called penalizing safe intersections in T or S. And phi TS is the area function defined as follows. To minimize ESIM and maintain the coupling of T1 and T2, we perform shape morphing between M and S2, and the shape T1 is defined from the distortion of T2. In the process of morphing, we employ a 2-level hierarchical interpolation algorithm. First, align M and S2 and compute their corresponding frame polygons according to the tiling vertices and feature points. Then we morph each interval of contour into intermediate shapes to obtain the optimized result of T1 and T2. The 4 tiling vertices stay fixed through the morphing process, thus ensuring the connectivity of tails in the final tiling. Here are the tessellation results. Given a dove shape as input our system generates the top 5 dihedrotilene results. The red-mouthed dog is a failure example, though it minimizes ethane, because the results are less meaningful due to large deformations in the simultaneous optimizations. Here are various dual-shaped tiling patterns generated by our system. We show a gradual deformation to achieve the sky and water pattern of Lin's work. The comparison shows that our method better preserves the control geometry and thus the shape visual appearance and quality, especially in the black frame where the two shapes are coexist. After obtaining the dual tessellation, we will generate the fabricable model by 3D modeling and the structure optimization. First, map the input 3D mesh model onto 2D parameter domain. Second, overlay the 2D tiling pattern onto the parameterized mesh and compute the Boolean difference between them. Then we map back the planar triangular mesh to 3-dimensional space and extrude each vertex to obtain a dual tail shell model. To increase strength, we perform a two-step optimization scheme. First, increase the area of connectors to enforce connectivity between the weak part and its solid neighborhood. We do this by locally dilating the contour of the solid shapes by a step size until reaching the upper bound. Next, we increase the thickness of the model for each weak surface vertex. The last stage is fabrication. Here are several fabricated 3D models with our dual-shape textures. A potential application is customized lampshade with a light source in the model. The light emanates through the hollow tails in the pattern, producing interesting light and shadow effects. We can also relax the mutual surrounding constraints for each tail, such that each element has connections with two neighbors that belong to the same shape type. Thus, both patterns can be fabricated in one connected piece. Our 3D manufactured custom I-shell blends with one rotation hinge on horizontal lily tails. The lily pattern can rotate with 1 degree of freedom, simulating the behavior of window blinds. We also adapt the tessellation result into a half-toning application due to their controllability and continuous tessellation of the plane. We control the half-toning amount by the tail skew parameter, since the tessellation structure is fixed. This is linear and corresponding half-toning by our swan and lily tessellation. In conclusion, we present a novel approach to model and fabricate I-shell dual-shape tilings from user-defined shapes. To conform with 3D printability requirements, our tiling commutation accounts for strength and connectivity. Of course, our approach has some limitations. First, it requires a generous zero input model, so we need to cut the closed model. It leads seams. Currently, we just put them in the hidden places of the model, such as the bottom and back of the bunny. Oh, sorry. Similar great distortion occurs in some sharp areas of high curvature, cause the tessellation texture was stretched in parameterization. Second, the above rules are limited because we just select those that generate good cold tails. in the future, we will explore more interesting potential rules. That's all. All data, results, and models are present on our project page. Thank you for your attention.
Thank you very much. Thank you for the presentation. Are there any questions from the audience, please?
Yeah, I have a question, if I may.
Yes, please.
So thank you first for the very nice presentation. I actually have several questions. So first, you issued in your last slide that you have problems with the seams on your model. So I was wondering what happens if you use a quadrillation algorithm that hides these seams via some optimization, or would it be feasible to hide the seams maybe at the bottom of the model? So that would be my first question. And the second question is, what happens if your quad mesh has singularities of low valence, say a valence 3 singularity, that would create new seams among your tiling tiles? So how do you ensure that for these singularities, your tiles still fit together?
That's a good question. As I have mentioned, now I have no idea to solve the seams. We just put the seams on the handle places of the model, and indeed, in the seams there will be some disconnections. So we sometimes we use the software to repair the model, but it only a little model that needs to be repaired. I think it's okay.
Yeah, thank you.
Thank you. There are some other questions from the chat. Could you check the chat box? Can you see the chat box, the questions from there?
Let me see.
If you could, I think somewhere on the lower, you may find the chat box there. Maybe I can read the first one. Is there a chance to replace surface parametrization by CVT? By CVT like segmentation?
Maybe it's a good way, but I haven't thought this method. If I have a chance, I will try this program algorithm to replace surface parameterization. I think it will work. Yeah.
Thank you. Any other questions, please? Maybe I may ask a question. Maybe I think in the field of graphics, there are many algorithms for example, for texture mapping. Is it possible to apply some of the algorithms from there for this application, from texture mapping? For example, if you have a piece of texture, you may also do similar like what you are doing, like tiling. First of all, actually it can also directly map to a mesh model. Is it possible to apply similar techniques like that?
I think the quadrant tessellation, we use quadrant tessellation is because the quadrant tessellation can give us more freedom of deformation, and the seams we have no good idea to solve them.
Thank you.
I have I have read this algorithm makes the integral quadrangulation, but I have no chance to try this algorithm, and I will try it.
Yeah, thank you very much. Are there any other questions, please? If there's no further question, we may switch to our second speaker. Thank you for the presentation.
Thank you.
Our second speaker will be Nuka Jisser Yulo. So if you could please share your screen already, please, if you could try. The title of the second presentation will be Sliding Basis Optimization for Heterogeneous Material Design. So if you're ready, so it's your screen now. So you can take everything.
All right.
Yeah, thank you.
Let me just start over again. Okay, so I'm Nurjan. I'm from Palo Alto Research Center, and today I'll be talking about our sliding basis optimization work for heterogeneous material design. Recently, multi-material designs have shown superior performance compared to homogeneous designs. And in addition to that, there are certain problems where we cannot really solve without involving heterogeneous designs because the homogeneous material design is just not capable of solving the problem, such as this DARPA challenge problem that is brought up by NASA. Here the problem is designing this gray region, the gray volume, basically designing the material distribution or geometry or both inside that region to be able to achieve a target thrust profile. But one major innovation that is aimed here is that to be able to basically eliminate that red insulation region. And how that happens is that we need to be able to ensure that the last burning surface is a cylinder so that the case portions are not exposed. So the portions of the casing are not exposed to the flames, and we don't need the insulation. So here on the right side here, you're seeing one geometric design that creates the thrust profile on the left. But one problem here is that the red regions shown there will be on the casing will be exposed to the flames of the remaining propellant parts that are still burning. So we cannot eliminate the insulation, only designing the geometry with single material. And realizing this challenge and through similar motivations in this work, we are presenting a practical method to design for design of multi-material heterogeneous fields. And we are showing it with this problem and also multi-material topology optimization. Let me go over the general material design optimization pipeline. Generally, we have an objective function and constraints defined on a discretized domain, such as this grid you are seeing here. And most of the time, our design problem is coupled with an analysis. Most of the time, this is the most costly part of the optimization problem, design problem. And for example, even if we are using the linear finite element analysis and structural topology optimization, this is the most costly part. And this part could also involve some complex physics. And it may be black box in most of the time in engineering collaboration due to some intellectual property issues. People just give these analysis as black box. And these problems bring up the issue of deriving the analytical gradients. Most of the time, they may be difficult to get, and they may be impossible to get because of some black box analysis programs. And in those cases, we can resort to numerical gradients, but they're not practical for large-scale problems. Let's say if we have a discretization with thousands, millions of elements, that means that we need to get the numerical gradient for each of these elements here. And it means that we need to do about like thousands or millions of additional analysis steps. And in this work, we are addressing this challenge by presenting this model reduction approach to reduce the number of optimization variables. So the idea is that instead of optimizing every single element in this field F, which could be in the thousands or millions range, we reduce it to tens and hundreds by representing this field as a combination of small set of basis functions. And this way, we are reducing the number of design variables without compromising the analysis quality, because we are still computing the whole field, but we are not optimizing for all of them. And in this work, we choose Laplacian bases for that, because they are pretty well known, and in the graphics community they have been used, and their properties are very well known. They're complete, meaning that they can present any field if all of the basis functions are used. And you can think of it, Laplacian basis functions as analogous to Fourier expansion in the discretized mesh domain, in the harmonic domain. And we can compute these Laplacian functions through eigenvalue problem, Laplacian basis functions through eigenvalue problem. And the eigenvectors, by concatenating the eigenvectors, basically we achieve our basis matrix. And one good thing about Laplacian basis is that, which is one of the main reasons why we choose Laplacian basis, is that weighted sum of these manifold harmonic bases can be used to describe the shape and material in a frequency domain. What I mean is that the key observation in our work is when we look at the basis functions computed on an object on a domain, what we see is that they form a spectrum, and they may be ordered from the lower frequency components to higher frequency components. And now property to achieve the sliding based optimization work that we are presenting. And in that, the idea is we start with a small set of basis functions, and then basically we are using only the only a small set of lower frequency bases at the beginning, and then we do the optimization for only those bases. And then we are sliding our window with a certain amount, and then we do the optimization on this green actively optimized part, but we are using all of the bases covered so far to represent the field. Basically, we do this we do this sliding operation until we achieve convergence. So basically, at each step, we have this green region as our actively optimized bases, and then we use all of the bases to represent this field. And one thing I want to point out here is that we usually get convergence using only a small set of basis functions, and this is how we are able to reduce the number of optimization variables and make the optimization a lot faster, and be able to solve otherwise intractable design optimization problems. I'm not going to go into the details of all of our algorithm. But one thing I want to mention here is that sliding-based optimization is a top-level framework that works with existing optimization methods. And here, this optimize step can be implemented using general nonlinear optimizers. And in our applications, we use SQP, sequential quadratic programming, but other gradient-based or sampling-based methods like interior point algorithm or simulated annealing or like genetic algorithms could also be used for this optimize step. And I pose the problem as being able to enabling solution of problems with large-scale problems with numerical differentiation with numerical gradients. But indeed, our sliding-based optimization speeds up differentiable problems too. For example, if the gradients are derived for the full resolution problem, meaning that if we have the gradients with respect to the full field variables, we can easily compute the gradients with respect to basis functions by just using the chain rule. And since the relationship between the field and our new basis weights are linear, we just have a multiplication with the basis function here. Let me go through the solid rocket fuel application and explain how sliding basis works. So, like I said, we have this application for NASA where we need to design the material distribution inside this gray area, and we also design this red surface, the initial surface that comes as byproduct of our simulation. And let me just show you a simulation of one of our results, and maybe it will give you a more clear idea of how this burn propagation occurs. So basically, we have the material distribution in this blue and red region. This blue and red color plot gives us shows the material distribution, and we have this green surface as our burn front. Basically, this burn surface propagates and becomes a cylinder at the end, which is the most important innovation in this work. And through this burning process, we achieve this desired target stress profile. And we formulate this problem as minimization of the difference between the optimized, meaning the thrust profile we get out of this by simulating the optimized thrust, optimized material distribution, and the target thrust profile. And our constraint comes from the fact that the last burn surface should be a cylindrical one. And how we solve this is that basically our sliding basis optimization pipeline is we have our discretization domain, we have our discretized domain, input domain to design the material inside, and we have the target stress profile. Then we compute the basis functions, and then we do our sliding basis optimization by starting with the only lower frequency basis functions, and then adding the higher frequency components as required until convergence. And at the end, we have our material distribution that gives us the required objective and constraint performance. Let's go through the thrust profiles that we achieve through these sliding basis optimization steps. So for this problem, we first start with the 20 bases. This number could change, of course, but in our applications, we use 20, and so that it was working well for our examples. We start with first 20 bases, and then basically we slide by a certain amount, and in this case, it is 15, and then we activate the basis functions that are in this green region again, and then again, we slide again, and we see that but as we incorporate more basis functions through the sliding basis optimization steps, we are getting better match with the target and optimized thrust profiles. And we do this again, and this time we have a little better match between the profiles. And here we have, as we incorporate new active bases, we have better convergence. And then here at this step, we get to convergence where we have less than 5% error between the optimized and target profiles, and I believe this was the error was 2% for this example. Just in summary, the idea is that we start with the first 20 bases and then incorporate another 15 by sliding and doing the optimization on that only active 20 basis functions. And we can see that the trust profiles match a lot better as we approach convergence. So I'll just show you a few examples. Basically, these are some other material distributions we got for different target trust profiles. Here another set of them. And here we are designing graded material fields. And so if you look into performance of our approach, we compare it with the fixed basis approach. Basically, the idea is that we are still using Laplacian basis functions, but instead of at each step optimizing a small number of them, if we use the optimize all of the covered bases in one pass, how would they compare? So here the fixed basis is already a reduced order approach, and when we compare, then we get up to 8 times speed up just adding the sliding basis idea on top of this fixed basis approach. And when we look at the objective values, they are usually comparable, and sometimes we can even see better objective performance with the sliding basis because we had this local perturbation, because we are basically doing a random initialization at each step and locally perturb the initial conditions. We also tried doing multi-material topology optimization here, and the idea is that again we are adding new higher frequency basis functions at each step, and you can see that here complexity increases as we incorporate higher frequency bases. And here, for example, for the record challenge problem, we had the graded material distribution, but here we can also achieve discrete material fields for this problem. And we also showed that we can optimize the material distribution inside the given domain. This time you're not optimizing the topology, but only the distribution inside the topology. Let me explain the difference between the conventional approach, meaning that optimizing the design for each pixel value on the grid, or our reduced order approach. One thing we see is that we can get comparable objective values with both approaches, but reduced order approaches significantly faster than doing the whole, than optimizing all of the pixels, all of the elements on the grid. And in a lot of the times, as we have large scale problems, it becomes a matter of not being able to solve the problem and being able to solve the problem if it's the difference between 1 day or 20, 30 days, let's say. Let me just quickly mention the sliding parameter, effect of sliding parameter we have here. So I was saying that we slide it by 15, we slide this window by 15. We investigate the effect of that to see how should we basically tune that parameter. And in our case, what we see that when we change these numbers, as we do after certain iterations, they all converge to some similar values. So in that sense, we can choose, it doesn't really matter that much if you are willing to do a certain number of iterations. But one thing is time increases significantly. And one good trade-off we have seen was that if you use the 75% of the number of optimized bases, for example, if you are optimizing for 20 bases, but if you only slide by 15 bases, it gives us a good trade-off for time and the error values. So in summary, in this work, we propose a versatile design optimization tool. And the main contributions of the presented work are, here we are presenting this optimization framework, which we call sliding-based optimization, to efficiently explore the parameterized design space. This is a practical material design method that enables doing the optimization with Laplacian basis with prescribed bounds without increasing the number of constraints. And this approach enables optimization of material distributions for new applications that are coupled with black box analysis. Before I stop the presentation, I just want to mention some recent developments. We also tested our algorithm on the traditional conventional structural topology optimization, and we basically optimized for the MBB beam problem and did this sliding based topology optimization using in total 50 bases, basically having only 50 optimization variables. And we also used top88 code, MATLAB code, using 10,000 elements. Basically, we had the same resolution in both of them, but with the conventional one, we had to optimize for all 10,000 of the elements. And what we see is we get comparable objective values. And one thing I will point out here is that the goal is not to match the geometry. Since we are using a reduced order method, we already know that we're not going to get the same geometry. But the idea is to be able to achieve comparable performance faster, so that we can enable new applications. And if we don't run into some intellectual property issues with the company, we might be able to release, we are planning on releasing this MATLAB code for this so that it could be used as a modular topology optimization system, but it is not a certain thing for now. So thank you all for listening. If you have any questions, please ask them now, or you can reach me at this email address later.
Thank you very much for the presentation. Are there any questions, please?
Can you explain why the basis functions are selected in continuous manner? Is there any special reason they have to do that, or you just for the sake of computation easily?
You mean instead of like we are sliding the window, you mean we could use some window here and then we could jump and then use other bases from there?
Yeah,
okay.
Exactly. This is what I mean.
Okay. Yeah, we actually thought about that. I think it could be very interesting for problems that require the high frequency component. For us, this sliding version seemed like the first initial approach to be able to basically cover the whole system, meaning that, for example, with the sliding approach, if we need all of the basis functions, basically we have a systematic approach to go through all of them. I guess the answer is yes, it can be done. For us, we thought about it, but we couldn't find a way to basically direct those jumps. We didn't have a way to understand which window we would jump to, so that we thought that we could have a little bit of overlap to get out of the local minimas and then basically try to cover the whole system in a sliding manner. But that looks like, I mean, that is something we considered, and that would be a good expansion if we had a good way of directing those jumps.
Thank you. I actually have another question. Like, how much percentage of speed up, or how many times speed up when we compare your result with the topology optimization?
For the topology optimization, so for our approach, I used MATLAB's SPM optimizer with numerical gradients, and for top88, it is incorporating the gradients, and it is also using the optimality criteria. So I don't think like the current, so basically what I had was using the numerical gradients for 50 optimization variables and using the all 100,000 variables with the most optimized optimization method for that one with the analytical gradients. I had the same optimization time, but I don't think it's a fair comparison, because like the fair comparison would be either me using the analytical gradients in the sliding based approach, which would make it a lot faster, or basically do the topadiate with numerical gradients, which would be probably terribly slow in MATLAB, and I probably wouldn't be able to do.
Right, thank you.
But yeah, thank you.
Are there any other questions, please? Maybe I ask one more. Maybe for the basis you are using a Laplace basis. In addition to Laplace basis, can you also use some other basis if you have any other suggestions?
Yeah, we thought about that. Basically, any other basis function that has the complete some properties which are the completeness, meaning that any field could be represented by that, and orthogonality, and then showing the spectral properties. Any basis that has these properties could be used. I guess Chebyshev functions has those properties. So basically any basis function that has those three properties can be used.
Thank you. Are there any other questions? If no, maybe thank you very much. Thank you very much for your presentation. Thank you. So, and now we can switch to next, please. Thank you very much for your presentation.
Thank you for listening.
Our next speaker will be Jing Qiaohu.
Okay.
Are you ready, Mr. Jing Qiaohu?
I'm ready.
Oh, that's great. Yes, yeah, that's great. Could you test your screen if you can share your screen already?
Okay.
Yeah, that's great. So our next speaker will be Jing Qiaohu. The title of the talk will be Cellular Structure Design based on Free Material Optimization and Connectivity Control. They are from State Key Laboratory of CAD and computer graphics from Zhejiang University. If you're ready, so would you please start your practice already? Thank you.
Thank you very much, Mr. Ma. It's my honor to be here to present our work. I shall be speaking for about 15 minutes to give a presentation on how to design a manufacturable cellular structure of valid geometry. I'm going to start with a general overview and then focus on this particular problem. At last, I'd like to finish by some numerical results and conclusions. Cellular structures are widely found in biological systems. Due to their attracting multifunction properties, they have been considerably employed in medical implant instruments or energy absorption protector, but their effective design still remains challenging. In this study, we want to construct a manufacturable cellular structure of valid geometry under certain volume usage budget. This is a critical issue in in-field design for additive manufacturing. There are main three challenges. Firstly, the computational costs are still demanding, as the homogenization has to be conducted for each microstructures. In addition, the traditional bi-scale optimization usually tends to generate completely homogeneous or totally heterogeneous structures. Thirdly, the scale separation assumption leads to geometric disconnection between adjacent components. A series of excellent work was proposed in previous studies. Liu and Shapiro focused on random heterogeneous material properties and generated graded material structures via texture synthesis. Liang used the analog material as guidance for digital material composition. Zhu et al. Pre-computed the achievable microstructure gametes, optimized the object topologies, and spatially varying material properties simultaneously. In this study, a continuous material density field, or equivalent to the Young's modulus, is usually computed following the traditional topology optimization, which constrains the degrees of freedom. Controlling the geometric connectivity between adjacent microstructures has become a critical issue in homogenization. Previous approaches are mainly based on geometric solution via fixing some key join points or geometric interpolations, which limits the physical property usually. Zong et al. Proposed to design geometrically continuous cellular structure by a variable cutting level set. Garner et al. Proposed a physics-based novel work that produces very promising results. However, the approach is not directly applicable here. Therefore, a separate two-step optimization approach is proposed in this study to help resolve the above issues. It first constructs an optimal field distribution of the material properties, which takes all variables of elastic tensors as design variables. This is in construct to previous approaches solely using the density. After this, we embed each microelement with an equivalent microstructure using an inverse homogenization approach. Okay, let's begin with the optimal material property field generation. Free material optimization, FMO for short, takes all parameters of the elastic tensor of each material point as design variable, as D in this formulation. It aims to maximum the stiffness of resulted structure, that is minimizing the compliance. Meanwhile, the solution should meet the static equilibrium equation and additional constraints. The trace of elastic tensors denotes the cost of the elemental material. The global trace constraint restricts the overall amount of materials distributed in the structure. And the finally derived solution can be considered as an ultimately best material distribution among all possible elastic continua. The middle figure is the material distribution of a cantilever problem. However, this original problem will generate some extreme elastic tensors, which is the darkest area in the color map, which usually make the subsequent microstructure design difficult or even impossible. Therefore, we impose additional manufacturability constraints to bound the minimal eigenvalues of elastic tensors away from zero, in case that any directional stiffness is too close to zero. The right figure shows the field distribution using a modified FMO. This leads me to my next point. This large number of different materials brings some challenges, including the huge amounts calculations in inverse homogenization and connectivity control between adjacent cells et al. We hope to reduce the material number and meanwhile maintaining high compliance fidelity. Here, we propose a post-processing clustering step. We chose hierarchical clustering and use Euclidean distance to measure the similarity between two tensors. After determining the cluster partitions, we do the second FMO to generate the corresponding cluster centers. Once the distribution of the optimal material properties is generated, we next embed the equivalent microstructures. Given a desired elastic tensors, the inverse homogenization is used to find the equivalent microstructure. The objective is minimizing the Frobenius distance of the homogenized and the desired elastic tensors. At the scale separation of the homogenization and the individual optimization of each group, two adjacent different types of microstructures are not necessarily smoothly connected. We thus introduce a set of intermediate cells, as the red cells in the bottom figure, to connect each pair of adjacent microstructures, and then optimize their physical property altogether. Consequently, when optimizing the microstructures, the elastic tensor matching is required for both desired original and the intermediate tensors. In this formulation, W measures the priority of the connectivity. The bigger W is, the better the connectivity is obtained. Take a look at the new microstructure. The physics-based connectivity control could produce smoothly connected cellular structure. Next, I'd like to move on to the numerical results to test the performance of our approach. Firstly, we test cases with or without manufacturability constraint in FMO. From left to right for the top figures, we increase this constraint, and we can find the compliance increase in either. Simply conducting inverse homogenization generally produces structures losing connectivity only if a strong constraint is imposed, however simultaneously lose the structural performance. And it's hard for the extreme elastic tensors from pure FMO to match the equivalent microstructures. Therefore, we impose weak manufacturability constraint, reduce the computational cost by clustering, and then add the connectivity in microstructure embedding. At last, we get manufacturable cellular structure of valid geometry. The effect of material clustering is tested under different cluster numbers and clustering approaches. Results on different cluster numbers at 3, 5, 7, and 10 are shown in the middle figure. We can find that the group with larger traces will be recognized first. With the increasing of the cluster number, the resulted compliance becomes closer to those of the referred FMO. This graph summarizes the effect of different clustering approaches. Our approach adopts hierarchical clustering and using Euclidean distance between the elastic tensors, which in black bar in the graph. The results demonstrate its best compliance amongst all the different approaches. Next, we will explore the relation between trace constraint in FMO and the volume fractions in inverse homogenization in depth. From left to right for the top figures, we increase the element trace bound and test the performance of the generated cellular structures. At first, we computed the potential maximum achievable bound by inverse homogenization, which is 0.3. Here we use the tensor distance d to measure the matching degree. As can be seen from the result, when the bound takes value of 0.5 and 0.8, the microstructure matching doesn't work well beyond the limit material budget of 0.3 because the tensor distance d is much bigger and here the d is small. In addition, with the increase of the bound, the material evolves along the major principal stress directions, which tells that the trace bounds affect the anisotropy of elastic tensors. From left to right for the bottom figures, we increase the volume fraction V0. The generated volume fraction remains around 0.7 when V0 takes value of 0.75 and 1. And the tensor distance are all around 0.006, which tells that V0 doesn't much influence the matching degree of elastic tensors. At the end, I'd like to show another example of L-shape. We get the optimal material distribution from FMO, cluster the elastic tensors, and embed a microstructure with connectivity control in video. Okay, that brings me to the end of my presentation. A novel framework of generating a manufacturable cellular structure on FMO field of target performance is proposed in this paper. The nice numerical examples mainly come from in the clustering approach to reduce the material number while maintaining physical fidelity, and the novel physics-based connectivity control. The approach can be further improved from the following aspects. The material clustering here requires a cluster number of 7 or 10 to provide a structure of high fidelity. Developing other clustering approaches utilizing the intrinsic physics of material property needs to be further explored. In addition, the study is mainly conducted for 2D cellular structure design, exploring its overall framework and the theoretical derivations. Its extension to 3D cellular structure is of more practical usage and deserves future research efforts. Okay, thank you for listening. And now, if there are any questions, I would be pleased to answer them.
Thank you very much. Thank you for the presentation. Are there any questions, please? Maybe I first ask a question. Possibly, I think it's different from your approach, but can you also use continuous functions for your design? And also, if you can, of course, and then what's the difference and what's the advantages between the two? For example, cellular structure design versus if you use continuous functions. Could you give any comments for that?
I'm wondering the continuous function means
for example, you are using cellular structure design. If you see some of the examples, actually you see the distribution of the material over the parts. Such a distribution could also be represented by some continuous functions. So my question is that, so what could be the limitations and advantage between the two if you use discrete structures versus if you use continuous functions?
I'm not really sure if we have tried to generate the completely heterogeneous structures by traditional bi-scale optimization. I'm not sure if this is what it means, but we have tried, but this completely heterogeneous structures by traditional bi-scale optimization, which is a most fair candidate benchmark. It has a close compliance to our result, but it loses geometric connectivity and its computational costs are much higher. In our test, the heterogeneous structures needs times with 9,000 seconds to generate a completely heterogeneous structures, and our approach just needs 700 seconds. Yes.
Thank you. Are there any other questions from the audience, please? Actually, we are earlier. So if there's no question, I think maybe that's all for today. First of all, thank you very much for your presentation, and also thanks to all the speakers of today, and also thank you all for attending this session. I think that's all for this session. Thank you. So
Thank you.
enjoy your conference, please.
Thank you.
Thank you. Bye-bye.
Thank you.
See you in some other sessions.
Thank you. Bye-bye.
Bye-bye.